Hi, good morning, and many thanks for giving me the opportunity to talk in this workshop. It's my first time here. I'm Raymond Zopp, Director Innovation and one of the founders at FlightKeys, a flight planning service provider, pretty new one. We started 10 years ago. I used to be a pilot myself for many years at Austrian Airlines, so I also have some flying experience. And what I'm showing here today is a novel approach to deal with low concentration ash. As I said, we are a flight planning provider, and our main product is actually cost-based optimization. So we base everything on cost and optimized trajectories with these algorithms with a very high success rate. And so I'm going to mostly talk about cost in this presentation. We heard already that entering ash clouds does something to the aircraft and mostly to the engines, so it can be costly. This is an example. That was the Kelat incident in Indonesia with an A320. Only a few minutes and actually not much abnormal on the engines during flight, but the engine had to be removed and the cost impact was probably several million US dollar. So changing an engine, we all know, costs something in the millions. So the conclusion is entering ash clouds can be costly. On the other hand, avoiding ash clouds can also be costly. In 2010, the well-known Eyjafjallajökull incident led to the canceling of around 100,000 flights over 6 days, with a combined cost for the airline industry of 1.3 billion euros. So this is definitely a costly event, and we definitely need to find ways to deal with such events in a better way. So we need to find a balance between the cost of flying through ash clouds and the case where we completely avoid ash clouds. So by balancing this, and that's our expertise at FlightKeys, we want to do it cost-based. And in the end, at FlightKeys, we actually found a way in a collaboration with Rolls-Royce. So Rory was very much involved, gave us lots of ideas. We found a way to add price tags to ash clouds. So not really to ash clouds, it's just as a picture, the cost will be added or applied to the damage in the engine, but to a certain degree, we apply cost. The latest studies, and again, I'm referring to Rory's work a lot, show that cost-based avoidance is feasible. And it's definitely much more efficient than strict avoidance of these events. So how can we do flight operations through contaminated air? In areas where there's no safety risk, and we've seen there are some areas that are typically much larger than the dangerous area, we can fly, but it has an impact. And the few areas where we really see a safety impact, they are very small. On the other hand, the modern jet engines, and the more sophisticated they are, the more we see the sensitivity to low levels of contamination in an economic way. So the impact is mostly economic. And in the Unitix project, that was a CESAR project in 2019, we participated where a large-scale simulation, simulating a volcanic eruption of Mount Etna, more or less distributing ash all across Europe. We demonstrated with our methods that almost all cancellations could have been avoided in such an event. So that would be a great thing to minimize the economic impact. And the basic concept that we developed is to project the future cost. So that's the probability of an engine change, of an earlier engine change than normal, and the increase in fuel consumption due to the deterioration of the engine. And we have found a mathematical model to directly relate the ash concentration, the duration, and the cost that will be expected in the future, and apply it to the actual flight. So that's what we do in all cost optimizations. We take some cost values and apply it and probably change the trajectory of the flight. So let's have a quick recap on the effects of engine contamination. We have the different contaminants on the left side, can be dust or volcanic ash, or even sulfur oxides, or even ice crystals. The primary damage is either self-repairing or irrecoverable. And the secondary effects, and that's what we are looking into now, is an increase in fuel consumption. And depending until the next repair or removal of the engine, this fuel consumption accumulates. So the increased fuel consumption is a cost that gets higher the longer the aircraft is still flying with this reduced efficiency. And we have a lifetime reduction. That means the engine has to be removed earlier, so we can calculate the remaining flight hours and the cost of the engine change and come up with a value of dollars per flight hour. Now, we have several assumptions in our model. The first assumption is, and that's a very crucial assumption, and it's physically pretty correct, the assumption is that the mass of ingested contaminant is proportional to fuel flow. Because we have a fixed fuel-air ratio, which means we can calculate the airflow through the engine simply by taking the fuel flow and multiplying it with the air-fuel ratio. So we already know how much air goes through the engine core. If we take the concentration of the ash, we can calculate pretty exactly how much ash goes through the engine core. So this is a very nice effect that helps us to get to correct calculations. Now, the next assumption is that in low concentrations, the damage done to the engine is more or less proportional to the amount of ash that has gone through the engine. So for the effect on engine efficiency, which affects fuel mileage, we assume a linear decrease per kilogram of co-ingested ash. And for lifetime reduction, we also assume a fixed number of hours per kilogram of co-ingested contaminant. So again, we have linear relationships that help us to come up with a linear function that is exclusively based on fuel flow, which is something we can calculate very precisely during flight planning. Contaminant mass, that's something that we need to get from the forecasters. In this case, for example, the QVA project, that would help us a lot to get these values. And exposure time, that's another thing that we calculate during flight planning pretty precisely. So we end up with a calculation that gives us a pretty good picture of the expected engine and the cost impacts of this damage already during flight planning. This algorithm has been tested in the Unitix project, and we would be ready to implement it in our system if the demand exists from the airlines to do it for our customers. To give you an example, this is a calculation for an A320. And what you can see here is on the horizontal axis, the Mach number, vertical axis, flight altitude in feet, and on the right side, the ash concentration over altitude. So you see there is a maximum of ash concentration at level 330 of 1 milligram per cubic meter, which is medium or even low ash concentration. And applying our algorithms, you can see that at Mach 0.77, we have more or less the optimum at level 390. So the green values show lowest cost, and that's total cost. That's fuel consumption, that's time cost, and that's the cost of the ash damage. And we have a much better value at low altitudes. At level 250, we can see that at Mach 0.77, or even at the lower speeds, Mach 0.73, we have a much better cost value. So this gives you an idea how the cost-based optimization works in such a case. So for this particular case, at this particular condition, it would be good to fly low and slow. Another example, an A380 at the medium weight with a similar ash concentration at the level 330 shows the optimum at level 410. You can see the really green values are at the higher levels. So that's the way the system is automatically finding the optimum vertical profile, and in the lateral plane, it's more or less the same because we do lateral optimization as well. So that's a point example what we are going to do in flight planning to find a minimum cost solution. The application of these algorithms are actually quite a multitude. First of all, it gives us a way to precisely monitor the total contamination exposure in very high precision. We can predict engine lifetime impacts. As Rory already mentioned, it could be a bonus system for maintenance contracts that can be monitored and put into the contract. Better decision support if we have a really high concentration event in a volcanic eruption. Risk assessment programs could be standardized by applying these algorithms in a general way. As already mentioned, it can be fully integrated in flight planning systems for cost-based trajectory optimization. And we can have automatic cost-based avoidance in high concentration events. This gives us a win-win situation where the engine providers on one hand can save on improved engine lifetime because ash clouds would be avoided in certain cases, even low concentrations, and aircraft operators would save on fuel consumption because the engine efficiency would be regained for a longer time. The current status is that in the cooperation with Rolls-Royce, we tried to find out how to come up with the best estimates of the cost functions. The algorithms are fully developed and have been demonstrated, integrated within our flight planning system. Ash cloud simulation data can be imported in the typical ways like GRIP data or other formats that are general. And in the Unitix project, we even published a paper where we demonstrated that by re-optimizing those 98,000 flights, in almost all cases, the cancellation of the flight would have been avoidable. So we came up with a cancellation rate of about 2 to 3% in such an event instead of canceling almost all of them. Last but not least, we have to continue the avoidance efforts during flight with tactical tools. And FlightKeys is also providing a tactical tool for the EFB on portable devices, iPads or so, where we do additional decision support in terms of economics. So the pilots have a clear picture, a visualization of the economics of the flight trajectory, of the flight profile, irrespective of ash or anything. So it's mostly fuel and time. But we can include other effects like turbulence, ash, and most recently, we also started to research into contrail avoidance. That's where our main research focus is at the moment. We calculate trajectories around areas where flights would create warming contrails, which is a severe climate impact of aviation. We do it similarly, both in flight planning, in the planning phase, and tactically in the cockpit. And we could imagine that we can use the same cost-based algorithms that we do for other effects for ash clouds. So the picture that you see here is the vertical profile with a contrail area, but an ash cloud would look more or less the same. We would probably give it another color. So pilots could have much better visibility, and that's really important. No matter how you plan a flight, pilots also need to know what are the critical areas where need the profile, where they need to stick as much as possible to the planned profile for a given reason. So that's what we are going to provide to pilots. Of course, these tools will use much more precise forecasts because we can use nowcasting in aircraft with satellite connectivity. And again, even in this real-time case, we can apply our cost-based algorithms to find the best trajectory around these areas. So we are offering to cover the entire flight cycle from early planning phase to flight execution in terms of operational assistance to dispatchers and pilots in terms of cost optimum trajectories. Next steps, we want to validate the assumptions, calibrate the damage parameters and algorithms. In effect, there is quite a good way to do it. We can take QVA data and combine it with the hindsight data of ash concentrations in the air and find the correlation. So this is something that can be done more or less with available data. And from that, develop the key parameters for most common engines. So this would help to fine-tune the algorithms over time. The next thing that needs to be done, and that depends on demand from our customers. If there is enough interest, we can fully integrate it. We have the knowledge and the algorithms and could offer that to our customers. Same thing to our EFB tool, Loretta. And so if you are interested in such a tool, just contact us and we can bring it to our roadmap and we would be happy to talk to you. It was a pleasure talking. And if you have any questions, just go ahead. Thank you.